Good afternoon, everybody. We will see today this evolution of climate models and tendencies. And many of you know me. I work in the National Institute for Space Research in São José dos Campos. That is an institute which has many departments. And, well, we'll talk about some features of climate models and projections. First, I'll give a brief introduction about climate models because some of you are not familiar with modeling, and it's only a brief introduction, okay? And then I'll talk a little bit about the difference of a climate model and Earth system model, and how to evaluate models. That is the main objective of this lecture, and some results of the assessment report 5 and CMIP 5 model simulations and projections. Okay. First, what is a climate model? So to build a climate model, we need to have a set of equations, a set of programs to try to represent the real climate. It's not an easy task because there are many processes in the atmosphere, in the ocean, and in the other characteristics of our globe. We'll see in a minute. So in a model, a climate model, we have a process, dynamical process, and these dynamical are related with circulation, related with winds, with temperature, with pressure, and there are physical processes, mainly related to radiation, convection, process of surface, and chemical process as well. Well, there are many reactions that occur in the atmosphere, in the ocean, and all these need to be taken into account in a climate model. So we see that the atmosphere and the ocean, or the globe, is a complex system. There are many interactions between ocean and atmosphere, between the land and the atmosphere, and all these interactions need to be taken into account in a model. So it's necessary to introduce in a model equations that are related to this, all this process. So we have only to simplify, 3 kinds of models. For example, atmospheric model. In one atmospheric model, we have all the process in the atmosphere, and the boundary conditions are prescribed. So we give to the model the sea surface temperature, that is the main surface condition, boundary condition. The conditions in the land, some of them are introduced as initial conditions, but there is no way of interaction between the atmosphere and the ocean. The ocean, we need to give the conditions of the ocean in order that the atmosphere can respond to that. But the sea cannot change based on the changes of the atmosphere. So is one model that we can see many features in this atmospheric model, but not all the features. Then we have a coupled atmosphere and ocean model. That is another kind of model that uses this atmospheric model coupled with one ocean model. So in this way, there is a possibility of the interaction between the two systems. And an Earth system model, that is the model that is has been considered in many climate change studies. This kind of model includes other kind of processes. For example, the dynamical vegetation. What is dynamical vegetation? The vegetation can receive the influence of the atmosphere of the ocean and respond to the atmosphere and the ocean. So it's an interaction between vegetation and the model and the climate, let's say. And another inclusion is carbon cycle. So we need to know the sources and the sinks of the carbon to try to represent the real climate. And this is included in an Earth system model. And another biogeochemistry, that is the interaction with the reactions that are occurring in the ocean, in the surface, related with the vegetation and other features of the sea, like algae or planktons. So you see that in this figure, we can see that there are many interactions. We need to represent all these interactions in a model. So it's not so simple. Although we can have this conceptual model in our minds. What is a climate model? The climate model needs to represent all these interactions. And we will see some of these features that some models can represent, or if they can represent well or not. This is the objective of an evaluation of models. And why this is important to climate change? Because many of these processes are changing based on the changes that are occurring in the atmosphere or in the ocean. I think that most of you know about the greenhouse gases. That's a concept, very basic concept. And if we increase the amount of CO2 or methane in the atmosphere, the radiation will be trapped in the atmosphere. So the temperature of the globe will increase. This is a physical concept, but we need to know how to apply this in a model. And for example, the evaporation or the precipitation can change if the temperature increases. The glaciers can melt with the increase of temperature. If we change the landscape, or if we change the vegetation, this will have an impact in the evaporation. And so there are many, many, many changes that we need to look at in a climate model or in an Earth system model. So the dynamical process are related, as I told you, with sea level pressure, wind components, temperature, wave gravity, and we introduce in the model dynamic equations, like equations many of you know, divergence, vorticity, the hydrostatic equation, the momentum equation, thermodynamic equation. All these equations can represent the dynamic of the atmosphere. And another set of equations are considered in the ocean. And for the physical process, like radiation, convection, clouds, and surface process, we have to introduce some what we called parameterization schemes. Why? Because the model resolution, which is the space between two grid points in the model, many processes occur inside or in a space less than this resolution. For example, clouds. What happened in a set of clouds? The resolution of the model can't resolve this process. For example, momentum flux. There are momentum fluxes in many grid points. And there are momentum flux between these two grid points as well. So how to consider all the momentum flux? So there are some schemes that changes this momentum flux to another variables that we can measure in the grid points. So this is the very simple, in a simple way, what is parameterization. So there are radiation, for example. We need to know the shortwave radiation, that is the solar radiation. We need to know the long wave radiation. We need to introduce the features of clouds, aerosols, water vapor, gases, mainly this kind of gases, CO2, methane, nitrous oxide, ozone, and other gases that are in the atmosphere. And for convection and rainfall, there are also several schemes. Each model can use one different scheme and verify if that scheme is doing well or not. So there's not one only scheme for each of this physical process. And this is in constant development. Every time a model is evaluated, it needs to improve for the next generation, and then all these schemes are being improved as well. And cloud microphysics, that is introduced in the recent models. We need to know the changes that happen in the inside the cloud. For example, to change to water vapor to liquid water. What are these processes? And the surface process that are very important in a model is everything that is coming from the land or the ocean to the atmosphere. So, as I said, momentum flux, heat flux, humidity flux, and all these fluxes are going to the atmosphere, and the atmosphere is getting this flux to change the circulation, the atmospheric circulation. So these are very important process. And the vegetation is also in this surface process. Because, for example, one place can have vegetation, for example, Amazonia region has a kind of vegetation. And another region, there is no vegetation. So the fluxes are very different from one region to the other region. And we need to include in the model all this information. What kind of soil there is in such regions, and what kind of vegetation, what kind of topography. Topography is important also. To run a model, to integrate a model, we need basically two things. One is initial conditions. We need to give to the model or to the equations the conditions that happens in, for example, one day. We need to give the wind conditions, sea level pressure condition, temperature condition for one certain day, for example. Why? Because all the equations have this DDT. What is? I know the variable in one time, and I need to know that variable in the next step of time. So I need to do dt, and if I have the first condition for the time 1, and I have the equation, I can have the other the same variable in another time. Okay. So this is for many variables: wind, temperature, humidity. And another second thing that we need is the surface boundary condition. So we need to have the topography. That's basic. We need to have the conditions of the land and the conditions for the ocean and the ice. Ai, estava querendo uma água que eu estou com a garganta seca. Obrigada. So for the land, we need to know these types of surface. So vegetation, snow, the soil, and the urban also. I think that the urban is not taking into account many models. Maybe one or two are trying to include this urban. But I think that this is one feature that should be included. We can talk about this in the second time of the lecture. About the ocean, sea surface temperature. The sea surface temperature is very important in a model because the sea surface temperature anomalies can introduce in the atmosphere changes in the circulation, changes in the convection. So many of you know about El Niño. That's, I think, the most known mode of variability in the global. The SST is very important. And the wind stress, the winds close to the sea are very important also because these winds can change the anomalies from one side to other sides. And we need to know the vertical structure of the ocean and the salinity, so many conditions to be included. And what are the features that need to be represented in a climate model? Well, first, the climatological atmospheric fields, like precipitation, pressure, wind, temperature, geopotential. Some of these large-scale features. We need to know if the model can represent the normal winds in one place, or, for example, the change in the winds in the monsoon of India, or the change in precipitation from winter to summer in many regions. So this is very basic. And also the representation of this seasonal, intraseasonal, interannual, decadal variability, and climate change also. And the representation of extremes, precipitation extremes that are very important also, extremes of precipitation, extremes in temperature. And the representation of teleconnection patterns as southern annular mode, north annular mode, that we will see tomorrow morning, okay? And ENSO influence also. So here is only, okay, thank you. We see that in the beginning of the modeling, we had only the atmospheric model and the ocean model. And the climate was represented by these two models only. And after that, we included sea ice, because sea ice, if we know that the white reflects very much more than the sea, the water, then this albedo should be included in the model, because this will have an influence on radiation. And the coupled climate model. So we improved this interaction between ocean and atmosphere. And then after that, we include some aerosol, because we know that if we have pollution in the atmosphere, depending on the size of the particles, the radiation, the solar radiation, will reflect more than if there is one place without pollution. So the solar radiation that arrives at the surface would be different. So this was another thing to include. And then the carbon cycle as well, because we need to know what are the sources of the carbon. In the 1990s, this CO2 increase, the increase was included also in the model. And then there is this dust and sea spray and carbon aerosols coming from the carbon. And dust that we know that, for example, in Australia and in North Africa, there are lots of dust being released in the atmosphere. And this dust also has some influence on the radiation. And the interactive vegetation is the dynamic vegetation that I told you, that the vegetation can have an influence of the climate and can influence as well the climate. So there is this kind of interaction. So many improvements in the model since the beginning of 96. So for evaluation, how to know if the model is good or not? Well, we can see the spatial patterns and see, for example, the seasonal variability. If the model can have this seasonal variability, for example, the precipitation in one region that we know that in the summer it has lots of precipitation, in the winter don't have precipitation, like southeast of Brazil, for example. In the summer there are lots of rain, and in the winter there are less rain. So if the model can represent these changes, I think that the model can represent the seasonal variability. But this does not mean that the model is good, because I have to look at other things. But it's a basic, if the model can't represent there, I need to improve this model. Yeah. So there is one way to look at the model, that is the bias. What is the bias? Is the model, a variable of model minus observation. So if I do this difference between the model and the observation, I can see if the model is overestimating or underestimating that variable. And there is another way to look at this, that is the root mean square error. That is almost like the bias squared bias. Why this? Because this root mean square error has only one sign, that's positive. Because the bias has positive and negative. But this error has the magnitude of the bias, let's say. And then we know which are the regions where there are more errors or less errors if we calculate this. So we can do also time averages to see if the model, how the model behaves. We can see the variability of some variables, see the extremes, trends. And there is one Taylor diagram that is a very useful way to see in one graph. We'll look one in a minute. And in this graph, we can include the standard deviation, the root mean square, and the correlation between two sets of data. And also, we can look at the modes of variability and teleconnections and see if the models can represent this. Okay. So we start now looking some results of CMIP5, which is a set of models that were run for the 5 assessment report. And many of you know about this CMIP5 multimodel. And if not, in the second class, we can discuss about this. And here is the first one there is the mean of surface temperature in the ocean and also in the land. Okay, so this is from the multimodel. What is multimodel? Is an average of all models of the CMIP5. And here is the bias. The difference between the model results and the error entering. Error entering is a reanalysis data set. The reanalysis data set is a set of data that uses a model but includes observations. So it's run with the real observations. So we can say that this set of data is an observational set of data. We cannot say that it's observations because it's not observations, but it includes all the observations. Well, many of you know about reanalysis, but I am talking only for the people who are not familiar with this set of data. So look at the difference between the bias and the root mean square error. There we have positive and negative values. And here we have only positive values. So there we can see many places where the model overestimates precipitation. And, here is temperature. Temperature here. I'll talk about precipitation in the other slides. So here we can see many places where the temperature is overestimated by the model. That is the red and yellows. And the blues are the places where the model underestimates. Okay? So there are, if you look broadly, you can see that in the Southern Ocean, the model overestimates temperature. And in general, it's underestimated in the North Hemisphere. And there are 2 regions where in the ocean, the sea surface temperature are very much overestimated. That is the west coast of South America and Africa. You can see these 2, I need to point here. These 2 here, this and this. That is an error that occurs in many, many models. And this feature has been subject of many studies. But still, they couldn't get out of this error. Still is there. And we see here in the when we look at the magnitude of error, that there are errors, larger errors here in this region. And this region is the region where there is the who knows which region is this region here. There is someone there from India, I think. You know what is in this region. Yeah, Himalaya or Tibet, very high mountain there. And here we have Andes mountain. And here we have Rocky Mountains. So it seems that in the mountains, this error is larger. But we don't know if it's because of the observational data set are not very good there, or if the model has some problems. So this is one thing that we need to see as well. Some differences. There are some differences between the observations. If you get era interim, if you get NSEP reanalysis, if you get another kind of reanalysis, there are some differences among them. So for precipitation, here's the same kind of analysis. This is the multimodal mean precipitation, and this is annual. Okay, there are differences of seasons, but here I'm showing only the annual because of the time. And but we see that the models can represent the main features. For example, the IPCC, the precipitation in Amazon region, the precipitation in the Indonesia region. That's a very active region for convection and precipitation. But here is the bias. And we see that there are many regions with a positive or negative. For example, the IPCC, well, there are more rain in the models than in the observation. And here is the changes are not related to era interim, sorry. Here is related to GPCP data that is considered as one of the best set of data because it contains the precipitation in the ground together with precipitation with information from satellites. So in regions where we don't have a good cover of the pluviometers, the information can come from the satellite. So this is why we can compare with the ocean also. But we see that there are some errors. For example, Amazon region, there is an underestimation of precipitation in the Amazon region and also in South America. And there is an overestimation over Indonesia and the Indian Ocean. These yellows here are very small bias, so only 0.5 yellow and 0.5 this light green. But and here we can see the magnitude. Hi.
Hi, Professor. I would like to ask if this bias is evaluated with the monthly data or the daily precipitation data, because the errors are very small. I believe it is monthly data.
Yes.
Monthly mean precipitation.
Yes, monthly data.
Oh, okay, thanks.
Because you do, well, here is monthly and then year.
Okay.
Okay. But here the scale is by day, millimeters per day.
Yeah. But the evaluation is done by month.
Yes, yes, yeah. And in this case is annual. Okay. And all these graphs are in the assessment report 5.
I have a question related with the bias, excuse me. When you did the mean bias between the observation and the ensemble of the models, so I think, I don't know if I have the truth, but you are comparing to different resolution. The GPCP is coarse than the resolution of the CEMIT 5 model. Do you think that it increased the bias in your results because you are compared to different resolutions?
Yeah, but what we do when we do this calculation, we regrid all the models to the same grid, because otherwise we couldn't compare. So if the model has a higher resolution, we will smooth to the lower resolution. And if the model has a lower resolution, well, I think that's better to have a high resolution, so you can do this regrid in a lower resolution than having a lower resolution to higher resolution.
So it means that it not affects in the assessment?
I don't think, because this is one problem. And for example, there are some models with high resolution. If they group all these models with the same resolution in one set and do the analysis, and then group other set of models with a lower resolution. But the assessment didn't do this. The CEMIP 5, well, they took all the models. I think that should be reviewed, this idea. I think so. And also, I think that there are some models that behave better than others in some regions. So, for example, for South America, I did some analysis of many models, and I thought that some models behaved better than others. So I took that to analyze. But when I found the results, they were very similar to the set of data of all models. So I think that this information were not lost. Yeah. So this is another way to evaluate the models, and I think it's a very interesting way. And this is in this paper, Mehan et al. And it is the model, the precipitation from the model divided by the precipitation of GPCP. And if it's more than one, the model overestimates. If the value is less than one, it underestimates. So here, there is this scale here, and if it's one, the model is perfect. So it's very difficult, but in some places we can see this kind of green, that the model could represent well the precipitation. And here there are some of the models of CMIP5. We can see many names here, and some of these are from Canada, from United States, from Miroc, for example, Japan and France, Australia. So this here is the Ensemble Me. Ensemble Me and Ensemble Median. The Ensemble Me is just taking the average of all models. And the Ensemble Median is a ranking of the values of the model, and then you take the middle of this ranking. So it's a little bit different from the Ensemble Me. But then we see, if we look this this ensemble, we can see, for example, let's say, let's take only the extreme errors, extreme overestimation or underestimation. For example, the red is here, means that the model overestimated this. And we see in the Rocky Mountains, in the Andes Mountain, again in the Tibetan region, South Africa, and the same happened with the median. And the most extreme negative error occur here, well, Central America, here close to the polar region, and also in the Indonesia region. And so there are many regions where we can see that the errors are not so high. There are still errors, but they're not so so big. So is one way to look at the behavior of the model. And now we have the seasonal precipitation cycle. This map is also in the assessment report. Wait.
Yeah, I have a question. In the northern figure, you have -1 or more than 1, so the bias, okay? But what the limit you consider for the a good model results?
Here I have only 0 to 2 because it's a rate. It's not a difference, it's a rate. If the model values are bigger than the observation, this rate is more than 1. And then the model overestimates. And if it's less than 1, underestimates. But, well, for example, more than 1.5 or less than 1.5. And in many studies, we calculate first the standard deviation to see if the standard deviation is greater than this error, then maybe the error is not so high. But if the error is greater than the standard deviation, so the error will be very big. Yeah. So here we have all these regions you can see divided by West North America, East North America, Central America, and so on. And here we have this cycle which is January, February, March, and precipitation. Here they plotted also the CMIP3, but let's look at the CMIP5, that is the red line. The red line is CMIP5 mean, the ensemble, and here you see there are 3 sets of data for observational precipitation. These 3 are in black. So we can compare the red line with the black lines to see if how is the model behavior. For example, let's take this one, West North America. The model is overestimating the observation there. But it has the cycle, the variability. This is important. The model can see this seasonal variability. Well, sometimes it is not the right value of precipitation for each month, but the variability is okay. But there are other, for example, let's take this one. South Africa is here, and is this one. We see that in the, well, Southern Africa is the same season as South America. So here is the summer, and in the summer there is an overestimation. But in the winter time, it's pretty good because maybe it doesn't rain too much. It's like south here, south, for example, South America has a very good cycle. Well, very distinct cycle during the year. More precipitation in the summertime, less precipitation in the wintertime, and the model can get reasonable well these cycles. But for example, north of Africa, that is here, in the we can see there are some months where the variability or the cycle is not so good, because in this season or in this month there is a reduction, but the model doesn't get this reduction. So here, for example, CAS is Central Asia. Central Asia has some problems also in this month. And this is with relation to seasonal precipitation, and here with temperature. And when we compare precipitation with temperature, we see that the temperature is is better represented by the models than precipitation. So the red lines, we see that is very comparable with the observations in almost all regions. I need to know the time, sorry. Only to see the... Onde? Ah, lá. Tá. A gente começou 2:00 e... 3:30. Então, mais 15 depois, tá. To see the errors in the sea surface temperature. As I told you, the sea surface temperature is very, very, very important for analysis of climate variability, climate change. So we need to know if the models can represent and how they can represent this variable. And here is there are many models, and the red line is the ensemble. And here's the error. Okay. And the error here is in terms of bias, is because it's the difference between the model and the observation. And the observation comes from this set of data here, has SST. And we can see that in this region, only to say, this is the zonal mean. In each latitude is calculated as zonal mean of sea surface temperature. And here is the equator and southern hemisphere and north hemisphere. And in the southern hemisphere, we see that this red line is very close to zero. So the error is not so high in the southern hemisphere, southern oceans. But in the north hemisphere, the errors are larger. And the model underestimates. Model represents the temperature less than the observations. And this is something we need to think when we analyze the projections, because we will see that the projections give higher temperature in the ocean and everywhere for the future. But the models underestimate. So if the model underestimates, these changes could be higher than the projections are showing. So here is the equatorial error. Equatorial, what is this? That instead of looking instead, será que pifou alguma coisa? Hã? Eu não mexi.
Eu sei. Fiquei pouco mais longe agora. Tá?
Tudo bem. And then we get the temperature in the equator, and we see in the equator how is the changes or the difference in the longitude. So here is the Indian Ocean, here is the Pacific Ocean and Atlantic Ocean. And in the Indian Ocean, we see that the red line is very close to zero. So the errors are not, well, there is small errors in the Indian Ocean. What's the good thing? Because in the Indian Ocean, we have the kind of Indian dipole that is an index. There is an index of sea surface temperature in one side of Indian Ocean and another side of Indian Ocean, which is related also with teleconnections. So if the model can represent well this sea surface temperature, it's good. But in the Pacific Ocean, we see two aspects of the errors. You see, in the west part of the Pacific Ocean and the east part of the Pacific Ocean, there is an overestimation of temperature. But in the Central Pacific, there is an underestimation of sea surface temperature. And this region is very important also to because it's the main place to influence the atmosphere in El Nino years, in La Nina years, and the Pacific Decadal oscillation is in this part of the ocean, and Madden-Julian oscillation, and many things happen in the Pacific Ocean that we'll see tomorrow. And then there are some problems with the models, because here we are looking all the models. And in the Atlantic Ocean, we see also a kind of different behavior in the West Atlantic, in the East Atlantic. In the West Atlantic, there is an underestimation, and the East Atlantic, there is an overestimation. So, in these two figures here, there is only the same as here, but only showing the CMIP 5 error compared with the CMIP 3, and all this shading are representing the dispersion of all the models. And the same happens here. Only that this figure is different from the others, because here is plotted the temperature, not the errors. So we can see, but we can see the same behavior. For example, here there is an underestimation in the Pacific and the overestimation in the East and West, and here the same in the Atlantic Ocean. Underestimation in the west part and overestimation in the east part. And also related to the ocean. Wait.
What is the reason that you use to compare the models with the observation? Okay. What is the reason that you use the HADI SST in order to assess the error, and you don't use, for example, the extended reconstruction sea surface temperature, for example, that is used to assess the index of the ENSO?
Yeah. Well, in this assessment, there are many analyses with one observation and another. But in this assessment, I think that there was this study of comparison of this multimodal with this kind of observational set, and they took this as an example, because in the assessment report we don't know, we don't do any new research. Okay. We take all the papers that were published with results, and we do an assessment of that results. So maybe this is the reason. Maybe there are not other papers which used the extended.
Okay.
But yeah, well, I use the extended. Yeah. But well, yeah.
Okay. Thank you.
And this is another variable that is considered in ocean. That is the ocean heat content. That's important also, because it informs all the heating that is inside the ocean. And this is the observation of this heating since 61 to 2005, observed, and the multimodal as well. And the red line is the CMIP 5, and we see that there is an agreement in the evolution of this heating. This first figure is in this 0 to 700 meters, or the first 700 meters of the ocean, the depth of the ocean, and this one here is the total ocean, or all the layers of the ocean. And both are showing an increase of this heat. But you see, if you take this total, the models, the multimodal, is underestimating the real changes. So the same that I discussed before. And then here in the lower depth, the model, the multimodal is comparable with the observations. Okay. So I'm not going to discuss all the numbers in this table, but just to show that the results of the energy budget from the models are reasonable good. For example, we look only these two columns here, and this is the variable. For example, top net solar radiation. The CMIP 5 multimodal gives a number of 244. And this is the observation that is published in the paper of Trainber, 2009. And it is not so, well, there are some differences, but the others, if we look at this one, and we see that's, well, there's not anything like one is 10, another is 200, or changes of sign or something like this. So the models can represent reasonably well the energy budget when we do the average, because as we saw in the other figures, when we take one model or comparing one model with another model, sometimes one is very far from the other one. And so there are many differences among the models. But when we do this average, we can get off many errors, and then always the ensemble is better than one model. This is the lesson. So here, for example, here I took one model that is a model from France, CNRM, and these results are in this paper here. And here is the precipitation difference of 2 seasons, extended seasons. And we see that some errors happen in this, larger errors in the Amazon region. But this error is found in many, many, many models. I think that the best model that I saw that the error is small, is the Hadley Center, this Hadgen M2ES model. And just to show you, I put here these results. This is the difference. We can't compare this with this because here it is plotted, one is green and yellow is -1. And between -1 and 1 is 0. Oh, but it's white, sorry, it's white. And, but here, the -1 and 1 is in this, well, it's not the light, red or light blue. So the 1 is here. For example, if you compare this with this, the errors in Hadgen are the -1 is concentrated in the north part of South America. And this model has the one, all this region here of Amazon, and very strong in the central part here. But in the other season, there are smaller than in the summer in the southern hemisphere. I know that there are many of you that live in the north hemisphere. So sometimes I'm saying summer, but when I do, I say summer is for December, January, February, but in the north hemisphere is summer is in our winter. So, and this is the surface temperature for this model, this French model, and we see that the problem is in the Greenland, and also again in the Tibetan region. Eu não estou enxergando lá as horas. Deixa eu ver aqui. Ah, falta um minuto. And then we see that, for example, this model, as I told you, some models can represent well some regions, some models can represent worse in another region. So we need to evaluate. This is the task of the evaluation. See if the model is behaving well and what are the problems. And we will see other features or other variables that need to be considered to know why the precipitation is not well represented, why the temperature is not well represented. So we will analyze the radiation, the problem in the clouds, and we'll do this after the break. There are lots of things to see still. Okay, there is some questions for this part, or we can.
Thank you for your nice presentation. My concern is about the performance of CMEP5 in reproducing rainfall in some regions, particularly East Africa, whereby we have bimodal rainfall pattern, the March, April, May, the long rains, and the October, November, December rainfall. So when you are doing an evaluation, it comes out that the CMEP5 models tend to underestimate the long rains and overestimate the short rains. Someone who happened to have a look at my work challenged me to use hindcast data in place of the historical data. That's for CMEP5. or something that I've not done, and it's not very common. I don't know how, if you have any experience about this and how it's likely to change my results.
Well, hindcast, yes. There is a project now that's called the Subseasonal to Seasonal project, where they are doing this kind of hindcast for each season, and for 10 to 45 days of forecasting. For example, 10, 20, 30 years, but is a forecasting for the past. This is the hindcast. This kind of thing maybe you are using. Or there are other projects doing this as well. But then, well, if you have only this kind of data to analyze, I think you can take in consideration the way that the model is doing. But first, you need to analyze the bias and the error, and maybe do a bias correction in order to remove the errors to get the right, or almost the right prediction or forecasting.
Thank you, Iracema, for your presentation. I had a related question. The spatial bias is a common problem in many kind of disciplines that work with spatial analysis. So I was thinking, when you show your slide showing the bias of several models, some of them kind of some of agreement, or some of them not. So for me, it was like, it seems that all the models are kind of a similar spatial bias, you know. So maybe no, but what I was thinking is, how would you discriminate when there's lack of observations to improve the initial condition, or maybe is we need a better parametrization, you know?
Yeah, well, I think that both. I think the parameterizations we will see in the next part, that the models can't represent well some of the physical processes. So to get a model that can represent all interactions between clouds and radiation and dust and aerosol and gases, the parameterizations need to be very good. And so I believe that the development of the models, the improvement of the parameterizations should improve the results. The initial condition, yeah, there are some places where we don't have too much information. For example, wind fields in the ocean. There are some, but it's not so good as over the land. So this could be a problem also. Yeah. So this is why there are some campaigns, sometimes collecting data in ocean, over the ocean, related to atmosphere variables and ocean variables, to analyze that period, because it's impossible, I think, to have all the time. But in the other way, there is now a possibility to have many information from the satellites. So wind fields can be collected, or the information of displacement of clouds can give the information of winds over the oceans. So there are many improvements in the observation side from the satellites. And maybe in the next generation of CIMIC 6 or 7, 8, they will include all this satellite information that can have a wide cover of observations. Okay, we have in the next part, we will have much time to see the other part of the talk and also to discuss, okay? Thank you.